irrationality of the product and quotient of non-zero rational and irrational numbers. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we explored the additive properties of these numbers, specifically, how adding or subtracting a rational number from an irrational number will always yield an irrational result. Now that we have a solid understanding of sums and differences, we are going to expand our investigation. Today, we will shift our focus to examine the behavior of multiplication and division when we combine these two different types of numbers, the rational and the irrational. The fundamental property. Now that we've recalled how addition and subtraction behave with these two types of numbers, let's move on to the core property we are focusing on today. The fundamental rule we are studying is this: the product or the quotient of a non-zero rational number and an irrational number will always result in an irrational number. However, I want you to pay very close attention to an important note here. The term non-zero is absolutely critical to this rule. Why? Well, think about what happens if we multiply any irrational number by the rational number 0. The result is simply 0, and as we know, 0 is a rational number. Because of this specific case, we must specify that this property only holds true when the rational number we are using is not 0. Keep this distinction in mind, as we are about to use this exact logic to build a formal proof by contradiction in the next few slides. Proving the product is irrational. Now that we have established the fundamental property and noted the importance of the non-zero condition, let's look at how we actually demonstrate this mathematically. To prove that the product of a non-zero rational number and an irrational number is indeed irrational, we aren't going to try and calculate every possible combination. Instead, we will use a powerful logical tool called the proof by contradiction method. To get our logic started, let's break this down step by step. We will begin by defining our players. Let us take a non-zero rational number, which we'll call r, and an irrational number, which we'll call x. Our specific goal for this proof is to show that the product of r and x, written as r times x, must result in an irrational number. Proving the product is irrational, continued. In this step, we use a technique called proof by contradiction. To do this, we start with step 1, the assumption. Instead of trying to prove directly that the product is irrational, we are going to assume the exact opposite of what we want to prove. So, let's temporarily suppose that the product of $r and $x is actually a rational number. To make our algebra cleaner, let's give this product a name. We will denote this product as $q. So, we can write the equation r times x equals q, where $q is a rational number. Keep this assumption in mind, because in the next few slides, we are going to show that this very assumption leads to a logical impossibility. Now that we have set the stage by defining our two players, the non-zero rational number $r and the irrational number $x, we need to move into the actual mechanics of the proof. Proving the product is irrational, continued. Now that we have made our initial assumption in step 1, that the product of our rational number r and our irrational number x results in some rational number q, we need to manipulate this equation to see where it leads us. In step 2, our goal is to isolate the irrational number. Since we established in the previous slides that r is a non-zero rational number, we are mathematically permitted to divide both sides of our equation by r. By doing this, we rearrange the equation so that x stands alone on one side, giving us x equals q divided by r. Proving the product is irrational, continued. Now that we have isolated the irrational number in the previous step, let's move on to step 3, where we analyze our result. Take a close look at the expression we just created. X equals q divided by r. To see why this leads to a problem, we need to examine the components of this fraction. First, remember our initial assumption from slide 4, where we assumed that the product was rational. Therefore, we know that q is a rational number. Second, the problem statement itself gives us the fact that r is a rational number. Now, here is the key mathematical principle. The quotient of any two rational numbers, provided the divisor is not 0, is always a rational number. So, looking back at our equation, since both q and r are rational, the entire expression, q divided by r, must also be a rational number. This is a crucial realization, because as we will see in the next slide, this result is about to clash directly with the facts we already know. Proving the product is irrational, continued. Now we reach step 4, which is the most crucial part of our proof, identifying the contradiction. Let's look at what we have gathered so far. From our work in step 2, where we isolated the variable, and step 3, where we analyzed the nature of the quotient, we have arrived at a conclusion that says x equals a rational number. But if we pause and look back at our original starting point, we remember the given fact that x is an irrational number. This creates a logical deadlock. You see, a number cannot be both rational and irrational at the same time. It's a mathematical impossibility. This clash between our result and our initial premise is exactly what we call a contradiction, and it's the key to finalizing our proof. Proving the product is irrational, conclusion. So, let's bring everything together for our conclusion. If you look back at the steps we just walked through, we started with a specific assumption in step 1. We assumed, for the sake of argument, that the product was actually a rational number. But as we saw in step 3 and step 4, that assumption led us directly into a logical dead end, or a contradiction, because it forced our irrational number to appear rational. Since a number cannot be both rational and irrational at the same time, our initial assumption must be incorrect. Therefore, we have successfully proven that the product of a non-zero rational number and an irrational number is, without exception, always irrational. Now that we've completed the formal proof, let's move on to slide 9, where we will apply this exact same logic to a concrete, numerical example using the square root of 2. Illustrative example, the case of 3\sqrt $2. Now that we have established the theoretical framework and the logical steps for a proof by contradiction, let's move from the abstract to the concrete. To see how this logic functions in a real-world mathematical scenario, let's apply everything we've just discussed to a specific, illustrative example. Our goal here is to formally prove that the number 3 times the square root of 2 is irrational. Illustrative example, continued. First, we start with step 1. We will assume the opposite of what we want to prove. So, let's assume that 3 times the square root of 2 is a rational number. Next, in step 2, we apply the definition of a rational number. If 3 times the square root of 2 is indeed rational, then by definition, it must be able to be expressed as a fraction, specifically, a is over b, where a and b are both integers, and we must ensure that b is not equal to 0. To put this into an equation, we can write that 3 times the square root of 2 equals a over b. Now, let's move into the actual application of the logic we just discussed. On this slide, we begin the formal steps for our specific example. Illustrative example, continued. Now, moving on to step 3 of our example. Up until this point, we have assumed that our product, 3 times the square root of 2, is a rational number, which we represented as a fraction, a over b. To reveal the contradiction, our goal now is to isolate the irrational part, which is the square root of 2, on one side of the equation. To do this, we simply divide both sides of the equation by 3. This leaves us with the square root of 2 equals a over 3b. Notice how the irrational component is now standing alone, which sets us up perfectly for the next step, where we analyze the nature of this new fraction. Illustrative example, continued. Now let's look closely at what this equation tells us. In step 4, we observe that since a is an integer and 3b is also an integer, which we know because b itself is an integer, the entire fraction, a over 3b must be a rational number. This is because, by definition, any number that can be written as a ratio of 2 integers is rational. Moving to step 5, this leads us to a very important realization. It implies that the square root of 2 is rational. However, we have a conflict here. We already know from our previous study of Theorem 1.3 that the square root of 2 is, in fact, an irrational number. Illustrative example, conclusion. Now we have reached step 6, which is the final piece of our puzzle. Look back at what we just discovered in the previous step. We ended up with the conclusion that the square root of 2 is a rational number. But, as we established earlier in our lesson, we know for a fact that the square root of 2 is irrational. This creates a logical contradiction, a situation where two opposing statements cannot both be true. Because our logic was sound, the only possible error must be our very first assumption that 3 times the square root of 2 was rational. Therefore, we can confidently conclude that 3 times the square root of 2 must, in fact, be irrational. Proving the quotient is irrational. Now that we have successfully proven that the product of these two types of numbers is irrational, you might be wondering if the same logic applies to division. The good news is it does. The logic we used for the quotient is actually identical to the logic we just applied to the product. Let's set the stage for this proof. Suppose we have a non-zero rational number, let's call it r, and an irrational number, which we'll call x to use our method of contradiction. We will start by assuming the opposite of what we want to prove. So, let's assume that their quotient, whether it is r divided by x or x divided by r, is actually a rational number. To keep our notation simple, let's call this resulting rational number q. As we move to the next slide, we will see how we can manipulate this equation to reveal the contradiction. Proving the quotient is irrational, continued. In step 1, we take that equation, $x divided by r equals q, and we rearrange it to isolate our irrational number. By multiplying both sides by r, we get $x equals q times r. This leads us directly to step 2, which is the turning point of our proof. We look at the right side of our new equation, q times r. Since we have already established that q is rational by our initial assumption, and we know r is a rational number by definition, we must apply the rule of rational numbers. The product of any two rational numbers is always rational. So, the expression q times r must be a rational number. Now, let's move on to the second part of our proof for the quotient. Building on what we established in the previous slide, where we assumed that the quotient of our irrational number $x and our non-zero rational number r results in some rational number q, we now perform the algebraic manipulation. As you will see in the very next slide, this creates a direct conflict with our starting premise, leading us to our final conclusion. Proving the quotient is irrational, conclusion. However, this directly contradicts the fact that we started with the given information that x is an irrational number. Since our assumption led us to an impossible contradiction, we must conclude that our initial assumption was false. Therefore, we have proven that the quotient of a non-zero rational number and an irrational number is always irrational. Now, let's bring this logic to a close. As we just saw in the previous step, we arrived at a result where x equals q times r, which would mean x is rational. This completes the proof for the quotient, mirroring the exact same logic we used earlier for the product. Key takeaways. First, always remember the non-zero requirement. As we discussed during our initial look at the fundamental property, the rational number must be non-zero. If we allow the rational number to be 0, the entire property breaks down because 0 multiplied by any irrational number simply results in 0, which is rational. Next, let's recap our two main rules. The product rule states that a non-zero rational number multiplied by an irrational number will always result in an irrational number. Similarly, the quotient rule tells us that when you divide a non-zero rational number by an irrational number, or even an irrational number by a non-zero rational number, the result is guaranteed to be irrational. Finally, I want to highlight the logical tool we used throughout this session. To prove these properties, the most effective and mathematically sound method is the proof by contradiction. We started by assuming the opposite of what we wanted to prove, and then showed that this assumption leads to a logical impossibility. All right, we have covered a lot of ground today, so let's take a moment to summarize the key takeaways from this lesson. Keep these points in mind as we move into our next topic, where we will look at some common pitfalls and mistakes to avoid when working with these types of numbers. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to touch upon some common pitfalls. As we've seen throughout this derivation, precision is everything in mathematics. There are 3 specific mistakes I often see students make when dealing with these types of proofs. First, please do not ignore the non-zero condition. It is very easy to overlook this, but remember that 0 is, by definition, a rational number. If you were to multiply 0 by pi, the result is simply 0, which is rational. This would completely break the property we just proved. So, whenever you are writing a proof or stating this theorem, always specify that the rational number must be non-zero. Second, be careful not to confuse the product of a rational and an irrational number with the product of 2 irrational numbers. Throughout this session, we have focused on the interaction between one rational and one irrational number. However, if you multiply 2 irrational numbers together, the result isn't always irrational. For instance, the square root of 2 multiplied by the square root of 2 equals 2, which is a rational number. Keep that distinction clear in your mind. Finally, watch out for incorrect algebraic manipulation. When you are performing the steps we practiced, specifically when you are isolating the irrational part of the equation, ensure you are dividing by the rational coefficient correctly. Your goal in these proofs is to maintain the form of a fraction, where the numerator and denominator are integers, to prove the result is rational. If your algebra is messy, your logic will fall apart. Keep these points in mind, and you'll be well on your way to mastering these proofs.